today, and apologies again for the having to reschedule the meeting, but I'm glad we managed and to find this new date with Francis. So Francis is currently assistant professor, right? Yeah, assistant professor at the University of Utrecht in the Netherlands, working on sort of climate adaptation in deltas. And she did her PhD at the University of Southampton, modeling river sediment flux also in deltas, and then did a postdoc there. And yeah, as we just said, if you want to work in deltas, it's really interesting to go to the Netherlands because they think about deltas a lot. So she did a postdoc in Utrecht and is now doing her assistant professorship. So we're really glad to have you, and I'm very much looking forward to hear your presentation.
Oh, thank you for the introduction. So yeah, I'm Francis, and as Stephanie said, my current position is titled Climate Adaptation in Deltas. And something I actually said in my interview for the position is that maybe climate isn't the main thing that needs adapting to in deltas. So I'll be talking a bit about that today, but most of this talk is a journey through the last 10 years or so of my research, trying to bring it all together. It's all quite large scale. I'll be looking at some specific deltas later, but most of my work is global or large catchment scale. So that's what you should be expecting. So, so that we all know what we're talking about, this is a delta. It's the classic delta, and why deltas are called deltas after the Greek letter. It's the Nile. And it's obviously very easily recognizable for most people. But there are deltas all around the world. And this is a map of using a very broad definition of deltas. So this is almost 11,000 deltas scattered around the world, highlighting the dominant force in each delta. And the dominant forces are either wave, river, or tide. And that often defines delta form. So the Nile, for instance, is wave dominated. It has a nice smooth coastline and protrudes. A classic river dominated delta is the Mississippi, if you can bring that to mind. I don't have a picture, but it's called the Bird's Foot Delta. And tide dominated deltas tend to be a bit smaller and have these nice large trumpet shaped river channels. So talking about deltas globally, as I said, why are deltas important, and why would we want to counteract relative sea level rise in deltas, as is the title of this presentation? So delta land use in deltas is actually much higher than in other areas of the world. And the graphs I'm about to show you are from a modeling data study. It was a paper that I did with Murray Scown at London University that came out last year. And we looked at 49 deltas worldwide, including the largest deltas, but also representative of other smaller deltas, for instance, a range of climates. And we modeled them over the 21st century under the 5 SSPs, and the SSPs are shared socioeconomic pathways, if you're not familiar with them. SSP1 has the least mitigation challenges and least adaptation challenges. SSP3 has the most, and SSP4 and 5 are high mitigation and low adaptation challenges, and vice versa. So you just have a spread of socioeconomic challenges. So for these first graphs, you can see here we have on the left people per kilometer squared between delta land and the rest of global land use. And as you can see, deltas have a lot more people than the world on average. And on the right, you have the urban land fraction, and you can see urban land use is also much higher in deltas than in other areas, but it's also increasing over the century. Similarly, at the bottom here, we now have the total cropland fraction, much higher in deltas, and irrigated cropland fraction. So these all indicate the very high human land use of deltas compared to other land globally. You can also see the changes over the century, some stationary, which I'll talk about a little bit later. For instance, urban land fraction increasing, but population actually really depends on the socioeconomic scenario that we're looking at. So that's very interesting. Looking a bit more at these deltas individually, so the 49 deltas. Those highlighted here in color are those with the highest values by the end of this century in 2100. So these are again the people per kilometer squared under SSPs 1 to 3. And this show that human pressures on deltas, human population is going to increase regardless of scenario from the current time we are now. Whether it peaks or not in the next century is up to the socioeconomic scenario we end up being in. Have the same as before, the urban fraction increasing in all deltas, some massively and some less so. Looking at the individual crop fractions, this is much more mixed results, as you can see, and those highlighted here actually have the highest change over the time period. And the same for irrigated crop fraction, but irrigated crop fraction actually shows a more standard increase over all of the deltas. And the mix here of the crop fractions, some increasing, some decreasing, some stationary, I said I talk about, and one of the reasons for this is that many deltas currently already have extremely high crop fractions. So a lot of the land is covered by agriculture. So there's already very little room to expand. There's very little natural vegetation. And this has productivity implications, right? You can't decrease the agricultural land use really without decreasing the productivity, because they're very productive environments. And this also means that there's not a lot of land use spare for anything else. So why would we want land spare for anything else in deltas? So let's have a look at the basics of delta elevation change processes to see how that works. So what is relative sea level rise in deltas? It's generally considered to be comprised of three main things, which is standard sea level rise, the sea rising, subsidence, which is the land falling, plus natural compaction, and that's actually the land falling due to natural processes. Subsidence is generally considered to be induced by human activities. A main one is groundwater extraction that induces subsidence. Here in the Netherlands and in many deltas worldwide, there's also gas extraction. In other places, there's oil extraction, and all of these cause land subsidence of much higher rates than would naturally occur with natural compaction. And all of these factors lead to flooding, salinization, and land loss. The other aspect of relative sea level rise, as you may have been able to tell, all of the processes that I just talked about, they cause delta land to sink relative to sea level. There's also a way that delta land increases relative to sea level, and that's aggradation. So the land gaining elevation. And this is mostly in deltas due to fluvial sediment delivery, sometimes coastal sediment delivery, but the bulk is from rivers, hence the name coastal river deltas. So that's in many deltas the bulk of what is aggraded on delta land. There is also the possible for organic accumulation, so plants growing in situ in the delta. They produce organic matter, which falls, potentially decays a little, but that also increases delta land elevation. But both of these, fluvial sedimentation and organic accumulation, are less possible in highly populated deltas, which actually comprises a lot of delta land, as I showed in the previous slides. So that makes both organic production and fluvial sedimentation difficult. So we talked about also the other processes in deltas, the pressures from sea level rise and upstream. And here there's from the same previous modeling study, graphs of regional sea level rise for some individual deltas. And this is under the RCP's representative concentration pathways, 4.5 and 8.5, which are named after the CO2 concentrations reached over this century. And as you can see, regional sea level rise increasing in all deltas in all scenarios. So that's not a huge surprise, but just to illustrate that, yes, there's pressure from the sea is increasing. We also looked at relative sea level rise, which is the regional sea level rise, so just the water level rise plus subsidence. And as you can see, that increases the rates of relative sea level rise hugely. This is all in meters, and the scales, the axes are the same on each, so you can compare. And the ones highlighted in color are the ones with the highest levels at the end of the century. And finally here, we also looked at extreme sea level. So this is a 1 in 100 year event, which is also noticeably increasing over the century. So not ideal for the sustainability of deltas. Looking at the upstream side, there were also changing and potentially increasing pressures. So these first graphs show the maximum daily river discharge per 30 years. And as you can see, this is a mixed picture for each delta. There's many more increasing discharges than decreasing. So that's potentially much larger floods in the future than we have currently. And here there's also projections of sediment flux, and the sediment flux is a 30-year annual average. And all these graphs are relative to 2010 levels. And in the river sediment flux graphs, actually the lowest sediment fluxes are highlighted in color. And what this shows is that there are some massive potential flood increases and predominantly sediment decreases. And as I said previously, you need the sediment to counteract the relative sea level rise. So the pressures on deltas from all of these forces are increasing over the century. So now I'm going to talk a bit more about what we did with the sediment modeling and give you some more detail on that. So sediment delivery is fairly well researched globally now over the last few centuries, and the pattern that's been found is that in many places in the world, sediment delivery in rivers has increased and then decreased, as is shown by these graphs here by Savitsky. So if you note the x-axis here, it's the present is actually on the left. So the time runs from right to left. But this theory of increase and decrease doesn't just happen over time, as illustrated by this graph I made for my PhD. So it's actually linked, the theory is that it's linked to economic development. So you can actually slide back down this curve. The idea is that as economies develop, we have deforestation and agriculture, mining and urbanization, and all of those increase sediment delivery in rivers. And then at some point, a peak is reached, and then we have other activities such as reservoir construction, flow diversion, river channelization, and soil and water conservation, which then decrease river sediment concentrations. And like I said, you can actually slide back down the other side of the curve, and this has been seen, for instance, with the fall of the USSR. When the land was abandoned following economic collapse, river sediment concentrations actually decreased again by sliding down the other way because there was agricultural abandonment and reforestation. So There's some recent work by Evan Dettier, which actually shows where various rivers are globally on this theoretical curve. So it does show that various rivers are on the increase or decrease depending on the state of their catchments. But to look at modeling this for places and times that we don't have data, like the future, we need data on these particular drivers. So reservoirs in particular have been identified as a main type of water engineering affecting river sediment. So here is data that I use for my modeling on global reservoir construction. So here the white dots are the existing reservoirs, and red dots are planned reservoirs, and the lighter red, the closer they are to being built. And the size of the circle indicates the volume of water that the reservoir would retain. As well as reservoir construction, I also use driving scenarios. So we come back to the SSPs, the shared socioeconomic pathways, and the RCPs, the representative concentration pathways. And for this research, I only used SSPs 1 to 3 from some downscaled ECSA data. And that uses population density and GDP as proxies for these anthropogenic drivers which affect river sediment. And for the RCPs, it's the temperature and precipitation effects obviously on the physical sediment production from the Hadley Centre in the Met Office. And this produced 12 scenarios, which I modeled for 47 deltas, which is a subset of the previous 49 that I mentioned, but excluding those on inland seas. So I only modeled deltas on the coastal ocean. And it shows over these 47 deltas over the century, the modeling showed a total decrease regardless of scenario. The decrease is more or less depending on scenario, but it's always a decrease. And generally what the scenarios show is that more climate change actually equals more sediment, because higher temperatures increase chemical weathering, which increases sediment concentration in rivers. And the scenarios also show that more socioeconomic challenges also equal more sediment. And that makes sense if you think about the curve, the theoretical curve that I showed previously, because if there are more challenges for socioeconomic development, catchments won't get as far along the curve to the end where sediment flux decreases. So that will actually result in more sediment for deltas, which is counterintuitively a good thing. And to look at these results a bit more closely, this is the map for individual deltas. So you can see that there's mostly decreases with some small increases. This map shows the filled circles are the average of the 12 scenarios, and the empty circles, if you can see some of them, are the maximum and minimum. So there are some deltas where the maximum and minimum have a different sign to the average. So in some deltas, it's not certain if sediment flux will increase or decrease. The one that generally stands out here to people is the Limpopo in southern Africa. It's the largest green circle. And I investigated this because it stands out, and it just turns out that the Limpopo is particularly susceptible to climate change, but it also has very little anthropogenic influence over the next century. So there's no major dams being built, no major increases in population or GDP. So that's why it stands out. This is the same data presented in a different way. So this is the average of the scenarios for each delta. The top graph shows the percentage change over the century, and the bottom shows the absolute change, but particularly on a log scale, because a lot of the rivers, the 47 that I looked at, it includes the Amazon and the Nile, the Ganges, some of the biggest rivers in the world, but also some very small ones. So if you try and plot it all on the same graph, it's very difficult to see. So again, this is very noticeable that it's mostly decreases, but the absolute change, interestingly, shows the importance for global sediment delivery to the coastal ocean. So you can see in approximately the middle of this graph, the bottom graph, is the Amazon, which is the highest bar. And you can see how large the decrease is in an absolute sense globally, but for the Amazon, that decrease is almost insignificant. So it's interesting to compare the significance for the individual delta versus the significance for the world. I also looked at the specific drivers of these changes, and it's very variable why sediment delivery is projected to change. So over the century, the socioeconomic drivers can cause positive change. It's a possibility in the model, but I actually see that it doesn't over the whole century. So socioeconomics from the beginning to the end of this century only decrease sediment delivery in the model. Climate change, as you can see, that's the middle blue color, mostly increases, and there's a few small decreases. And obviously, dam construction can only reduce sediment delivery. And like I said, very variable between deltas. You have things like you can either have very large changes which cancel out. So for the Krishna here, it has very large socioeconomic change in a negative sense, but also very large climate change influence in a positive sense, and those just cancel out. But you can also have the Volta here at the end. The rivers are alphabetical here, and the Volta has very large changes in every single driver, which massively decreases its sediment load. So bringing all of the data back together again and looking at the global numbers, these are the contributions of each driver in total for all of the rivers between the beginning and the end of the century. And these are the 4 different climate scenarios, which you can see there is a small difference between the scenarios. Sorry, the center column is obviously absolute, and the right column is the percentage change. And these are all obviously positive changes for the sediment. There's also the socioeconomics now, which have negative changes, and at the bottom, reservoir construction, which is then clearly the key global driver of sediment flux changes. Since moving here, I had a master's student, Vibran van Ellen, and he did a very similar thing, but using a new scenario, which I didn't include, SSP5. So he did a combination of SSP5 and RCP 8.5. So some extreme challenges. He also included dam construction scenarios, but crucially, he looked at a slightly different time period. So where I looked at the average, the change between 1980 to 2009 to 2070 to the end of the century, he looked at the change between this decade and the last decade of this century. And that gives some interesting results. So this is the data that I showed you earlier of the percentage driver contributions with the larger time period. And in the right-hand column are Vibran's results. So you can see here that actually a lot of the changes have already happened. So you can see it a little bit for the climate change for the RCP 8.5. It was 11.6% of the contributions from my work, but if you start instead in 2020, it's only 8%. But crucially, the very bottom, we have the reservoir construction changes, which for my work found it's a contribution of 30% of the sediment decrease, but for his work only 9%, which indicates that about 20% of those changes have already happened in the period basically between when I started my PhD and a couple of years ago when he did his master's thesis. So that shows how many of the reservoirs have potentially been built in those last 10 years, and how little choice there now is to avert that sediment decrease. I'm now going to have a look at the situation for some individual deltas. So this is the Bengal in Bangladesh and India, and there's this lovely satellite image with these huge sediment plumes off the coast. And looking at this is a DEM of the area, so it is extremely low-lying. It's a huge low-lying area. The very darkest green you can see in this picture is over 3 meters above sea level. So as you can see, there's huge areas of the delta which are actually below 3 meters above sea level. In this image, you can also see at the bottom, there's a stripe of red going up, and this is interestingly called the swatch of no ground, which is a marine canyon, and that it's thought receives a lot of the sediment that the rivers now discharge, and it's why the delta isn't a lot larger than it is, because all of the sediment is going into infilling this marine canyon. But the Bengal Delta is fed by 3 main rivers, so the Ganges, the Brahmaputra, and the Meghna, which you can see the basins of in this inset. The Ganges and the Brahmaputra are obviously the largest. And the delta is so large that it has these various areas of the delta under different influences, which are also coloured in. It's just to highlight that it's a very large and complicated delta. It's a really interesting place. And what we did is we modeled flood sedimentation under various conditions. So we modeled the change between the poldered and the natural state. So right now the delta has a lot of polders, a lot of dikes and flood protection. So we modeled flood sedimentation in those conditions, and also what would happen if all the polders were removed. So this is in the natural state, on the left under average flood conditions, and on the right under extreme flood conditions. So you can see that is very different, and in the extreme there's a lot of sedimentation in the southwest of the delta. And then there's also in the poldered state, and you can see how different the sedimentation is. So this sedimentation is what builds up the delta elevation and enables it to counteract relative sea level rise. You can see that the polders are obviously receiving no sediment in any flood scenario, because it's assumed that they all hold. But this obviously massively disturbs the natural state of the sedimentation. So the changes are, for instance, in the retained sediment, it's increased by 6 to 9%. If you just remove all the polders, the area of sedimentation is increased by about 30%, but it does depend on the flood condition. So some important numbers for Bangladesh specifically. There is, depending on the flood condition, 400 to 1,200 million tons of sediment delivered to the delta. And 90 to 600 million tons of that is actually retained on the delta. This is again according to this modeling that we did. That gives an average sedimentation of 5.5 to 7.5 milliliters over the areas which do retain sediment. And currently, relative sea level rise is around 5 millimeters per year. So if you have a flood per year, it looks like it counteracts the annual relative sea level rise. So great. But there is more than 8 millimeters per year of climate-induced sea level rise likely over the remainder of the century. And that's in the strongest mitigation scenario. That's the best case scenario regarding sea level rise, which shows that the flood sedimentation, again, assuming one major flood per year, isn't enough even with the current sediment delivery. And as we've seen, the current sediment delivery is not stationary and it's not stable. So we'll look at that in a bit more detail for the Ganges and Brahmaputra now. So these are measured recent sediment delivery data. And this is just the Ganges plus the Brahmaputra fluvial sediment fluxes, excluding the Meghna because it's much smaller. And you can see for the last several decades, this steady downward trend in sediment delivery. This downward trend is also seen for the water fluxes, which is important because it means that floods might actually be less reliable in the future because you need enough sediment to raise the land to actually promote sedimentation, but you also need enough water for the delta to flood to get the sediment onto the land. And these are going back to the sediment flux projections. So this is from the global modeling shown earlier, plus some historical reconstructions, and it's the average annual sediment delivery. So the first bar is pristine sediment flux for the Bengal Delta. The second bar is recent, so a little bit lower. Pristine, it was in theory without any anthropogenic activities. The rest of these bars are the 12 scenario projections, and as you can see, they're all much lower, very little variation. I did some updated modeling for the global risk work that I showed at the very start, using the same RCP and SSP scenarios. So the light colors are the 4 RCPs for SSP3, and the dark colors are the 4 RCPs for SSP1. And this data shows the 30-year averages. And this updated modeling shows that it's not actually as dire as I thought with the global modeling, but it's still pretty bad. It decreases by about 50% from the start of the century to the end of the century. So not good news. I also looked at the flood projections, and this is specifically for the Ganges. And again, this one is the 30-year maximum flood discharge from a model ensemble median. And the trends here are less clear than sediment, but in both RCP 2.6 and 8.5, floods could actually be increasing in size. And if you combine that with what I said earlier about the overall water discharge decreasing, that's particularly worrying because it could mean that obviously overall there's less water, but floods are higher. So that suggests much drier periods combined with much wetter periods, which is very difficult for people to adapt to, considering, as I previously showed, all of the people living in these areas and the intense land use. So we'll now move on to have a little look at another delta, the Mekong, which I've been working on quite a lot for the past few years. And this image was actually taken during a flood. You've also got the plumes of sediment off the coast, but if you look upstream, so the top left of the image, you can also see very muddy flood water. And that's so this is in Vietnam and Cambodia, Vietnam having the majority of the delta and the upstream floods in this picture being in Cambodia. So again, it's very low-lying, as the vast majority of coastal river deltas are. And I'm going to talk to you a bit now about some work I did with Philip Minderhout, who's a subsidence expert at Wageningen University. And we looked at relative sea level rise in the Mekong Delta, just using, as I showed you before, that basic equation of global sea level rise, natural compaction, subsidence, fluvial sedimentation, and organic accumulation. So the Mekong River passes through multiple basin countries and has some huge issues of transboundary sediment fluxes due to dams built by upstream countries. Vietnam obviously has most of the delta, but almost none of the river. So has very little control over what happens to the upstream river. And this is a close-up of the Vietnamese Mekong Delta. There's Can Tho, which is the city in the center of the delta, but also Ho Chi Minh City is on the edge, so actually has very similar processes happening there. This image also shows the various branches. There's the two main, the Mekong and the Basak, but I think it splits out into 9 by the time it reaches the coast. And this is a graph that I like because I made it, but it shows most of the sediment, the work on fluvial sediment that's been done for the Mekong recently. So the underlying black lines are what I modeled for the work that me and Philip did. And these numbers are without calibration. So this was just straight modeling it and see what comes out. To validate this, we looked at the measured estimates and ranges. So you can see those in green. That nicely, the modeling work and ranges fit very well with what's been measured recently. So that's great. And in blue, you can see other projections that people have done for the Mekong. And there's a few that are a bit more optimistic than ours. But generally, we all agree it's going down. And with the fluvial sediment projections, we combined them with estimates of other relative sea level rise factors. So these are the 5 bars of the 5 relative sea level rise processes and deltas that I explained earlier. And the first set of 5 here is again the pristine values for the Mekong. So historically, the sediment the fluvial sediment was much higher. The organic accumulation could have been significant, although there's quite some uncertainty there. There was obviously no groundwater extraction induced subsidence, but normal natural compaction. But overall, in the grey bar, you can see the delta was gaining elevation. And the following 4 sets of 5 bars are our projections into the future up to 2050. So you can see in the scenario average, things just get worse. And there is no scenario where the elevation doesn't decrease in some way. And that causes the projections of the average delta elevation to look like this. So obviously the gray is the range of scenarios. The black line is the average of the scenarios. And this graph also shows the impact of the individual drivers. So it shows that subsidence, this extraction-induced subsidence, is the biggest driver of elevation loss. And the increases from fluvial sediment delivery and organic accumulation are not enough to balance it out. So coming back to this diagram that I showed you earlier, what if we had sedimentation strategies? What if we tried to help along the natural processes and increase delta elevation ourselves? So that's what we started with for this research for the Mekong. We did some very basic calculations of what if we restrict sedimentation areas, we add up all these numbers and see what happens. So we created these 4 scenarios of potential sedimentation areas instead of looking at the whole delta as for the previous graphs. So these would give concentrated sedimentation, and we selected these particular areas for various reasons. So the upper flood zone, that is where that's the historical flood area. That's where the river is used to flooding. The second, the lower flood zone, that seems to be where floods are being pushed in the modern delta for various reasons, like diking upstream. The third, the low elevation splay, that's because it has this area in the delta has extremely low elevation. It's actually mostly below sea level, so it really needs some additional elevation. It's also a very agricultural area, so in theory, it's one of the easiest places. There's no major urban infrastructure that would be flooded. And finally, there's the Can Tho buffer. So this is a very small area around the city of Can Tho, which is on the river, with the idea of creating kind of a natural dike ring to protect the city. So 4 different scales. And these are the maps of potential sedimentation results. So this this first line is just the DEM of the Mekong Delta as it is now. This is the potential change in elevation in 2050, assuming no sedimentation strategies. So the purple colors are decrease, orange colors are increases, and as you can see, there's no actual increases in this scenario, obviously, without sedimentation. This line is the potential elevation of the Mekong in 2050 with our suggested sedimentation strategies. And you can now see for the smaller areas where the actual sedimentation strategy is. But for the larger ones, the top two, it makes almost no difference because the sediment delivery is so small and the area is so large. So the only place that you can really see the difference is with this very small buffer around Cantot at the bottom. And these are the average elevation changes of the areas. So this illustrates that it's really unrealistic to rely on sediment if the other drivers of relative sea level rise are unchanged. So that's predominantly global sea level rise and human-induced subsidence. So looking a bit closer at these sedimentation enhancing strategies, what do I mean? What do they look like? This figure is from a perspective paper recently published in One Earth, which I'll come back to later. And these are some specific strategies and how they work. So on the right, you can see the basics are that there is a land surface, and in some way, sediment-laden water is allowed onto the land surface. It slows and deposits sediment, which raises the land and creates new elevation. And on the left, you can see various ways this is accomplished. So in A, there is a standard dike breach. In B, there's a more engineered dike breach where you have a secondary dike to prevent further flooding. For C, there's vegetation planting, which is a classic method of slowing water and encouraging sedimentation. D, it's the same, but on the coast, which is also possible. And E, there's these engineered structures, which again encourage water slowing and sedimentation. And a closer look at these. So you have various kinds of engineering. So for river sediment diversion, that's often more engineering. Tidal flooding, B, that's often the removal engineering. That's very popular in Bangladesh. You can have, as on the bottom, like I said, there's sedimentation structures and vegetation planting. So this paper was led by Jana Cox, who was a PhD at Utrecht. And this was a review of projects, sedimentation enhancing strategies globally to see what's been done and the results. And this was possible because there's really not very much published. So we did a full review of everything globally. And this is a map of the strategies we found of the various types in various places. So these are some graphs as a result. So the top is the sedimentation rates of projects plus the rates of sea level rise under RCP 2.6 and 8.5. And as you can see, most of the projects enable sedimentation at rates higher than global sea level rise. So that's very promising. The bottom graph is the sediment volume versus the monetary cost. And that obviously shows there's a huge range of both cost and sedimentation and sedimentation rates. So it's very possible to select appropriate sedimentation enhancing methods considering local delta environments and socioeconomic factors. But there are, as suggested, many challenges for these sedimentation enhancing strategies. This is a diagram of some of the biophysical challenges. So you have these declining sediment supplies that I've talked about a lot. You have sea level rise and its effects of, for instance, salinization. There's changing coastal sediment dynamics, subsidence, which I've also talked about. There's also unknown or changing parameters like tidal amplification. And as I said at the start, there's also this lack of adaptation space. A lot of deltas are very occupied already. In addition, there are parallel issues for society, and this work we did, I won't read all of this out, but just to say this work we did was very transdisciplinary. So this is a lot of work done by my colleagues on the socioeconomic, governance, and legal barriers, and obviously they all interact in various ways. But they are just as important as the biophysical barriers, which I've previously been talking about. So finally, we came up with some kind of suggestions for how to solve these challenges. And this figure is an attractive culmination of that work. So it presents three different methods of delta management. And on the left, we have the defensive. So the classic hard engineering with fixed dikes and storm surge barriers and sea walls, polders, which are low-lying and protected with urban areas and infrastructure. We have intensive land agriculture, groundwater oil and gas extraction, land drainage, with increasing costs due to relative sea level rise, channel engineering, channelization, straightened and maintained waterways. In the middle, we've illustrated the current paradigm best practice. So this is an integration of soft engineering and natural protection, like vegetation and dunes, some temporary sedimentation polders. As I illustrated previously, you can have these secondary dikes to prevent further flooding, some hard engineering to protect infrastructure, some natural protection, low dikes with sluices to enable some water-land connection, some rivers reconnected to floodplains, and all of that enables a certain amount of ecosystem restoration, like wetlands. There's a little less intensive and hybrid agriculture because of this. And on the right, we have what was basically the end goal of this thought process, which is a fundamental change in river delta management. So this involves large-scale land-water connection with coasts and rivers free to migrate. It involves full sediment connectivity, sediment and water connectivity. There's space for ecosystems through managed realignment, adapted cities with raised infrastructure, repositionable and floating structures to enable sedimentation. There's more frequent land cover change for the same reason. There's different modes of agriculture and aquaculture, for instance, floating farms, extensive and hybrid agriculture, for instance, rotational farming and flooding, with new modes of land governance, products and production systems, crucially, including business models and sustainable resource management. So, to conclude with my key points, sedimentation is the only way deltas can gain elevation relative to sea level. In addition, local management of sediment resources is required for sedimentation as adaptation due to human activities, particularly dense populations and drivers of relative sea level rise. Sediment delivery to deltas is often reducing currently, but that could be improved by international management. And management of subsidence and sea level rise make sedimentation enhancing strategies much easier. And with that, I conclude. And there's a list of references in case there was anything interesting that anybody wanted to look up.
Great, thank you so much. Round of applause from everyone, I guess, even though you can't hear it. Yeah, thanks a lot for this very interesting presentation. Really enjoyed the kind of look forward into this interesting future. Really nice graphic as well. So thanks very much. We do have time for questions, and I'm pretty sure there will be some questions from the audience. So if you have a question, then you can raise your hand or maybe just write in the chat. We have the first question from Uwe.
Hello. Yeah, great presentation. The main question that always comes to mind is, for how long do these scenarios work? I.e., this lovely slide at the end. There comes a point where you can't maintain a delta, basically, or where I work on a much smaller scale, sort of some salt marshes. So at some point, it just doesn't work anymore. And at what point does one say, well, the only way is actually to move away from this? For how long does one sort of carries on with this sort of make-believe we can sort of manage this? And obviously in the Netherlands, that always is a good question, because moving an entire country is a bit more difficult than just realigning a few properties.
Yeah, that's a really good question, and there's probably quite a long answer, probably a whole nother talk on this. But what comes to mind is that, so my PhD work was just on the modeling fluvial sediment delivery to deltas, and at the end of that, as you've seen in this presentation, it's all going down, and basically it's hopeless. In a few thousand years, there will be no deltas. There's not enough sediment. It's not going to work. So that prompted in me some kind of professional depression, in that, why am I doing all of this? What's the point if there's actually not going to be deltas? Like you say, at some point you have to abandon. So that's actually why I pivoted my work to the adaptation, because there are however many, 500 million people is the number that's often quoted, 500 million people living on deltas worldwide currently, and they can't all just leave. So what can we do with the resources we have available, resources including sediment delivery, to enable them to stay on deltas, if that's what they want, for as long as possible, to even improve their lives? Because a lot of these large deltas are in developing countries with people who really are just trying to improve their basic standards of living. So what can we do to enable that, to basically improve delta residents' lives and make delta as sustainable as possible? And that's how we got to this final, basically very radical scenario of fundamental delta management change. And I wouldn't want to put a timeline on when this stops working, but I think this gives the maximum length of time for people to plan to leave. Whereas the traditional delta management kind of doesn't admit the possibility that leaving is going to have to happen at some point. Whereas if you're living in a place where you're aware of the environmental change and you're not just walling it out, it gives people the kind of, the creative space to say, okay, is this situation still working for us? And not say, well, we're behind the dikes, so it's fine, until there's potentially a massive catastrophe. So that's my answer to that. And I'm currently working with Marjolein Haasnoot, who's she worked on the IPCC, but she works a lot with these delta adaptation pathways, and also the idea of retreat or managed realignment, or whatever the good word is now, and how to get from the place we are now and the management strategies we have to whatever it is that we want in the future. Like, do we want to maintain our current lifestyles on deltas? Can we change it to extend our habitation of deltas? And do we want to do that? Yeah, so a long answer, but like I said, I think there's a lot that can be said about that.
Okay, thank you. So maybe instead of, I know that's not easy to do, but maybe instead of having these three figures, they could be like little movies where you also see the dynamic within the adaptation, but difficult to do, I guess.
Yeah, this was already quite an undertaking. The original sketch of this was just me, like sketching it, and I'm not an artist, so this is already a vast improvement on that.
It looks great. Do we have other questions? I have a quick question because I haven't worked as much in sort of more tropical countries, and I'm wondering about aquaculture, so shrimp farms and things like that. Do they increase or decrease sediment availability in the rivers? I really have no idea, so I was just wondering.
Shrimp farming is an interesting one, and it's very prevalent in the Mekong. So I'll give an answer from that perspective. I wouldn't want to speak for all shrimp farming everywhere, but currently, shrimp farming in particular is massively increasing in the delta due to reasons like salinization and relative sea level rise. Unfortunately, classic current shrimp farming, which is industrialized shrimp farming, also worsens the problems of salinization and relative sea level rise, in addition to being highly polluting. So once you've converted your rice field to a shrimp farm, you have some years of shrimp farming, and then the place is too polluted to continue to farm shrimp, and you can't revert back to rice. So then it's ruined. I have been working. I had a master's student actually last year who went to the Mekong Delta and did measurements of sedimentation in shrimp mangrove farms. So this is a kind of a hybrid method of shrimp farming with the idea that it is more sustainable, it has some mangrove cover, to look at whether that kind of system could be sustainable. The main problem with it is that farmers want to know the level of their land in relation to both the groundwater and the river, which is fair enough because they need to manage the water levels for the shrimp. So what they tend to do is anything that is deposited in the shrimp pond, which is they open it to the rivers, so that they do get new sediment. Anything that's deposited is then dredged out again. Because it's much easier for shrimp management. So the challenge there is to work out, a farming system which can retain sediment. There's additional problems like if they open it directly to the river, then they're afraid of pollution or diseases from upstream coming in and affecting their shrimp. So then they often have a settling pond, and then the settling pond is instead dredged, potentially for dikes or for housing construction, even to elevate housing. So it's possible, but I don't actually have any answers yet.
Yeah, I was already sort of suspecting that the problem is probably a lot more complicated than a simple answer, so don't worry. Do we have any other questions? Reginald, I think you're muted. Let me...
Yeah.
Oh,
okay.
Here we go.
I've just done that. Yes, brilliant presentation. Thank you very much for that. I'm quite staggered by the predictions you make. It's sediment transport problems are really quite difficult, and you need to be able to predict your sedimentation from land to your delta really quite accurately to be able to do these kinds of predictions and so on. So how confident are you that you're getting the sediment deposition within the delta right?
Yeah, it's a good question. So I would say it depends on the model you're using. As I kind of caveated it in the beginning, most of my work is global or large scale. So I would actually say that for my work and for my previous work, I wouldn't take the exact numbers of sedimentation too accurately, and that's with the exclusion of the work that I showed in Bangladesh. Because they use different models. So the models that I use are generally pretty good on the large scale. And then to make sure that you feel confident in your delta sedimentation results, you then have to switch to different models that are fine-tuned to your specific environment. And I would say what you actually need is sub-delta models for most of these deltas. Because, for instance, there's lots of really great, for instance, salt marsh models or field scale models, and where you can feel, okay, we have a reasonable grasp on the millimeters scale of the sedimentation and the processes, but that's not so possible for delta scale because there's just so many different environments and processes. So I think I don't know if it's possible, but we might be missing a delta scale model, which includes all of these processes. So the catchment input from upstream, the changes in the sea and ocean coastal stuff, as well as the land and coastal ecology, and, for instance, management practices like the tidal river management or anything. So yeah, I agree, it is important, and we're working on it.
Thank you for that. Am I right in thinking that probably most of these models are regressional type models based on measurements that have been made in these systems and then extrapolated, or are they really hydrodynamic sediment transport type models that have led to these predictions?
There's both are available, yeah, which I think is also interesting and important. And I've done it a few times to basically use the different kinds of models for the same problem and compare. And there's often not huge differences, which is quite reassuring. Yeah, so I don't do a lot on the small scale, but for the large scale sediment delivery models, that's what I found to be the case.
Okay, well, thank you very much for that.
Thank you.
Great. Yeah, thanks very much from me again to Francis for the interesting presentation and everyone for joining. And before you leave, I'll quickly hand over to Jonathan to introduce the next speaker.
Yeah, great. So our next talk will be on the 1st of February. It will be given by Tim Smythe from Plymouth Marine Lab, who will be talking about artificial light at night and pollution sources in marine ecosystems. So hopefully you'll be able to join us then. And if you were late for today's presentation or weren't able to attend or want to catch up on any of the previous webinars, they'll all be available on our YouTube channel very soon. And thank you, Francis, once again for an interesting talk.
Great.
Thank you
Thanks,
for inviting
everyone.
me.
And yeah, hope to see you next month. Bye.
Bye.